Dear student, welcome in the class of mathematics. In this video, you will learn homogeneous linear differential equations. See the very important question. Define homogeneous linear differential equation and find its solution. This question may be asked as define homogeneous linear differential equation and write the method of solving it. So see the answer. Dear students, in last unit, we have seen linear differential equation with constant coefficient. The equation d raised to n y by dx raised to n plus p1 d raised to n minus 1 y by dx raised to n minus 1 plus dash 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 plus pn minus 1 dy by dx plus pny is equal to capital X, where p1, p2, p3, pn minus 1, pn are constants and capital X is function of small x. This equation can be written as f of d into y is equal to capital X, and we say this equation as linear differential equation with constant coefficients. We have seen how to solve such an equation in details and have solved some examples also. Now see what is the homogeneous linear differential equation. The differential equation of the type x raised to n d raised to n y by dx raised to n plus p1 x raised to n minus 1 d raised to n minus 1 y by dx raised to n minus 1 plus dash 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 plus pn minus 1 x dy by dx plus pny is equal to capital X, where p1, p2, p3, pn are constants and capital X is function of x is called homogeneous linear differential equation. Now, what is the difference between linear differential equation and homogeneous linear differential equation? If you observe homogeneous linear differential equation, in each term, power of x and order of the derivative both are same. In first term, power of x is n and order of derivative is also n, both are same. Similarly, in second term, power of x is n minus 1, order of derivative is n minus 1. Continue in this way. Last but one term, power of x is 1, order of derivative is 1, and in last term, power of x is 0 and order of derivative is also 0. So this is the main difference between homogeneous linear differential equation and linear differential equation with constant coefficients. Now we have to find the solution of homogeneous linear differential equation. So we have to see the method of solving it. So first, consider that homogeneous linear differential equation and give this is equation number 1. We have to solve this homogeneous linear differential equation. So first we have to reduce this homogeneous linear differential equation to the linear differential equation with constant coefficient. So for that, we have to put some substitution. So put z is equal to log x, that is x equal to e raised to z and capital D as d by dz. And therefore, dy by dx is equal to dy by dz into dz by dx. Here we use chain rule. Value of dy by dx is equal to dy by dz into dz by dx. In denominator, we take extra dz. So in numerator, we adjust it dz. This means we use here chain rule, and here dz by dx, as z is log x, so take derivative with respect to x on both sides. So value of dz by dx is 1 upon x. Now put that value of dz by dx here. So we get dy by dx is equal to dy by dz into 1 upon x. So this is the value of dy by dx. Now transfer this x to the left hand side, so we get x dy by dx is equal to dy by dz. As a d by dz is capital D, so you can write this is capital D into y. Denote this is as equation number 2. Now d2y by dx square, you can write d2y by dx square as d by dx of dy by dx. Now see this equation. In this equation, value of dy by dx is equal to dy by dz into 1 upon x. So put this value here. So this is equal to d by dx of dy by dz into 1 upon x. Now we have to find derivative of this product. So use u into v formula. So this is equal to first derivative of u, v as it is. So 1 upon x means v. So v as it is, derivative of u, d by dx of dy by dz plus u as it is means dy by dz as it is, derivative of v, that is d by dx of 1 upon x. Derivative of 1 upon x with respect to x is minus 1 upon x square. And see this first term, here again we have to use chain rule. D by dx into dy by dz, you can write this as d by dz into dy by dz, and derivative of z with respect to x means dz by dx. Again use chain rule for first term. So this is equal to d2y by dx square is equal to 1 by x as it is. Here d by dz, dy by dz into dz by dx. We use chain rule, and then dy by dz as it is, derivative of 1 upon x, which is minus 1 upon x square. Take this d by dz inside 1. And so this is equal to 1 upon x d2y by dz square, dz by dx, that value is 1 upon x, and then minus 1 upon x square outside dy by dz. And so we get d2y by dx square is equal to 1 upon x square d2y by dz square minus 1 upon x square dy by dz. Now multiply by x square on both sides. So we get x square d2y by dx square is equal to d2y by dz square minus dy by dz. As you know, d by dz is capital D. So this term is capital D into y, and this term is capital D square into y. And so we get this is equal to d square y minus dy. Take out y as a common. So this is equal to d square minus d into y. Now take d as a common here also. And so we get x square d2y by dx square is equal to d outside d into d minus 1 into y. Now give this is equation number 3. As already we have find equation 2, which is x dy by dx equal to dy. So you get first x into dy by dx is dy. Now we get x square d2y by dx square is equal to d into d minus 1 into y. Similarly, if we continue like this, we get x cube d3y by dx cube is equal to d into d minus 1 into d minus 2 into y. Compare these three equations. So we can find this for rth term also. And so continuing this way, we get x raised to r d raised to ry by dx raised to r is equal to d minus 1 d minus 2. Continue like this. Here x raised to 1, so we get 1d. Here is x square, so we get 2 terms. Here is x cube, so we get 3 terms. As here is x raised to r, so here we get r term. In last term, we get d minus 2 here. Means this number 2 is less than 1 of 3. So here we get, in last term, the number less than 1 of r, that is r minus 1. And so x raised to r dr raised to dr y by dx raised to r is equal to this. Now take this minus sign inside 1. So this is equal to x raised to r dr y by dx raised to r is equal to d into d minus 1 into d minus 2. Continue like this, d minus r plus 1 into r. Now we have to put this in equation number 1. What is equation number 1? This is our equation number 1, that is the homogeneous linear differential equation. We have to put these values in equation number 1. As we get the formula for x raised to r dr y by dx raised to r, so put r is equal to n, we get a value of x raised to n d raised to n y by dx raised to n. If we put r is equal to n minus 1 here, then we get value of x raised to n minus 1 d raised to n minus 1 y by dx raised to n minus 1, and continuing in this way. So first, value of x raised to n d raised to n y by dx raised to n is, put r is equal to n here, so that value will become d into d minus 1 into d minus 2 into d minus n plus 1. So this is the value of first term, plus this p1 as it is, value of this x raised to n minus 1 d raised to n minus 1 y by dx raised to n. So put here r is equal to n minus 1. So we get p1 into d minus 1 d minus 2. Continue like this, d minus n minus 1 means n plus 1, and then plus 1 means it is n plus 2, and then value of, continue in this way, put value of x dy by dx, which is dy, and then in last term we get p and y, take out y as a common, and so we get this is equal to x. But what is x? Log of z, x is equal to log of z, means z is equal to e raised to x, means on this side we get function of z. And so we get this new equation. We can write this equation as, see, this is the polynomial in capital D, so we can say this is f of d. So you can write this equation as f of d into y is equal to capital Z. Means this is the linear differential equation with constant coefficients in two variables y and z. We can solve this differential equation by our previous method. Solving this linear differential equation, we get relation between y, z and constant. And then putting the value of z as log x, lastly we get the relation between x, y and constant, which represent the solution of homogeneous linear differential equation. So this is the method of solving homogeneous linear differential equation. Now we have to see examples. So see the first example. Solve x square d2y by dx square minus x dy by dx minus 3y equal to x square log x. So see the solution. This is differential equation 1. Here we observe that power of x and order of derivative both are same in each term. And so this is the homogeneous linear differential equation. So put z is equal to log x, that is x equal to e raised to z, and capital D as d by dz. And so we get x into dy by dx is equal to capital dy, and x square into d2y by dx square is equal to d into d minus 1 into y. Now put all this in equation number 1. So equation 1 becomes d into d minus 1 into y minus d into y minus 3y is equal to value of x, which is e raised to z. So here we get e raised to z bracket square and then log of x, and log of x is z. Now take out this y as a common and d inside 1. So we get like this. Take out d inside 1. So this is equal to d square minus d minus 3y equal to e raised to 2z into z. And so we get d square minus 2d minus 3 into y is equal to e raised to 2z into z. Now this is of the type f of d into y is equal to capital Z. Means this is the linear differential equation. Now here auxiliary equation is f of d is equal to 0. F of d means d square minus 2d minus 3. So put that value. So we get d square minus 2d minus 3 equal to 0. Now find out the factors of these. And so we get the factors d plus 1 into d minus 3 equal to 0. Separate that two factors. So we get d plus 1 equal to 0, d minus 3 equal to 0. And so we get d is equal to minus 1 and d is equal to 3. So these are the roots of the auxiliary equation. And therefore, complementary function is c1 e raised to m1x plus c2 e raised to m2x. Now put the values of m1 and m2. We get cf is c1 e raised to minus 1x plus c2 e raised to 3x. Denote this is as equation number 2. Now we have to find pi, that is particular integral. And you know pi is given by the formula pi is equal to 1 upon f of d into z. F of d means 1 upon d square minus 2d minus 3, and z means e raised to 2z into z. So we get pi is equal to 1 upon, write down the factors of f of d which we have already defined. So here we get pi is equal to 1 upon d plus 1 into d minus 3 e raised to 2z into z. Now this is of the type 1 upon f of d e raised to x into capital X, and we have seen that result as 1 upon f of d e raised to x into v is equal to e raised to x outside. Instead of d, write down d plus a, and so we get 1 upon f of d e raised to x into v is equal to e raised to x 1 upon f of d plus a into v, where v is function of small x. So we can use this result here. Instead of d, we have to write d plus a and take the term of e raised to x outside. So similarly here, this e raised to 2z will get outside, and instead of d, we have to put d plus a means d plus 2. And so we get pi is equal to e raised to 2z outside 1 upon, write down d plus 2 instead of d, so we get d plus 2 here, d plus 2 here, so 1 upon d plus 2 plus 1, d plus 2 minus 3, and this z as it is. 2 plus 1, this is 3, 2 minus 3, this is minus 1, and so we get pi is equal to e raised to 2z into 1 upon d plus 3 into d minus 1 into z. take out this product, and so we get pi is equal to e raised to 2z 1 upon d square plus 2d minus 3 into z. Now take out minus 3 as a common here, and so this is equal to e raised to 2z upon minus 3 1 upon 1 minus d square plus 2d upon 3 into z. We take minus 3 as a common from denominator. Now see this one, transfer this denominator to the numerator. So pi is equal to e raised to 2z upon minus 3. So you can write this is minus e raised to 2z upon 3 into the bracket 1 minus d square plus 2d upon 3 to the numerator. So this will become raised to minus 1 into z. Now see this bracket. This is of the type 1 minus x bracket raised to 1 minus 1. We have seen two results. Expansion of 1 minus x bracket raised to minus 1 is given by this one, and expansion of 1 plus x bracket raised to minus 1 is given by this one. Say this term as x, so this is of the type 1 minus x bracket raised to minus 1. So we have to use here first result. So using this result, we get pi is equal to e raised minus of e raised to 2z upon 3 1 plus x, x means this term, d square plus 2d upon 3 bracket raised to 1, then x square, so we get d square plus 2d upon 3 bracket square, and continue in this way, and lastly outside z. So pi is this one. Now take this z inside 1, and so we get pi is equal to e raised to minus 2z upon 3 into square bracket 1 into z, that is z, then d square plus 2d upon 3 into z, and then d square plus 2d upon 3 bracket square into z, continue like this. If you take this z inside 1, so here you require two terms, d square of z and d of z. D of z means derivative of z. Derivative of z with respect to z is 1. So d of z is 1 and second derivative of z is 0. So here we can find at most second derivative. The derivatives of order 2 and greater than 2 all are 0. Now see the second term. In second term, if you find the expansion of d square plus 2d bracket square, the first term is d raised to 4. That value is 0. In middle term, we get 4 d cube. D cube is again 0. And in last term, we get d square, which is again 0. Means the second term is 0. As second term is 0, so third term and next all terms are 0. And so we get pi is equal to minus of e raised to 2z upon 3. This z, take this z inside 1. All these next terms are 0. Derivative of z is 1. Second derivative of z is 0. So you can write this as pi is equal to e minus of e raised to 2z upon 3 square bracket z plus second derivative of z 0. 2 into 1, that is 2 upon 3. So this term will become 2 by 3. And so we get pi is equal to minus of e raised to 2z upon 3 into the bracket z plus 2 by 3. So we get the value of pi. First already we have find complementary function. Now here we find pi. And as we know, general solution is given by y is equal to complementary function plus pi. Now put the values of complementary function and pi here. So we get y is equal to c1 e raised to minus z plus c2 e raised to 3z plus e raised to minus 2z upon 3 into the bracket z plus 2 by 3. Now put here value of z. As we know, z is log x, means x is equal to e raised to z. And so e raised to z is equal to x. As e raised to z is x, here you required e raised to minus z. So take raised to minus 1 on both sides. And so we get e raised to minus z is equal to x raised to minus 1. In second term, you required e raised to 3z. So take raised to 3 on both sides. So here we get e raised to z raised to 3 means e raised to 3z is equal to x cube. If we take square on both sides, here we get e raised to 2z is equal to x square. Now put all that values of e raised to z, e raised to minus z, e raised to 3z, e raised to 2z here. So we get y is equal to c1 x raised to minus 1 plus c2 x raised to 3 plus minus of x square upon 3 into log of x, because z is log of x plus 2 by 3. Now here observe that this is relation between x, y and constant. So this is the general solution of given homogeneous linear differential equation 1. That is the solution of that differential equation. Now see the second example. Solve x squared d2y by dx square minus 2x dy by dx minus 4y is equal to x squared plus log x. So write down that equation and give this is equation number 1. This is the homogeneous linear differential equation because order of x and power of x and order of derivative both are same in each term. As this is homogeneous linear differential equation, so put z is equal to log x, that is x equal to e raised to z and capital D as d by dz, and so value of x dy by dx is equal to capital dy and value of x square d2y by dx square is equal to d into d minus 1 into y. Now put all this in equation number 1, so we get d into d minus 1 into y, then minus 2 into dy minus 4y is equal to value of x square, which is e raised to 2z, into 2 value of log x, which is z, so it is 2z. Now take out y as a common outside here, so we get d into d minus 1 minus 2d minus 4 into y is equal to e raised to 2z plus 2z. Now take this d inside one, make that calculation. So you get d square minus d minus 2d minus 4 into y is equal to e raised to 2z plus 2z. Minus d minus 2d, it is minus 3d. So finally we get d square minus 3d minus 4 into y is equal to e raised to 2z plus 2z. Now observe this, this is the differential equation of the type f of d into y is equal to capital Z. Means this is the linear differential equation. As this is linear differential equation, its auxiliary equation is given by f of d is equal to 0. F of d means d square minus 3d minus 4. So put that value of f of d, which is d square minus 3d minus 4 equal to 0. Now find out the factors of this one. So we get two factors, d plus 1 and d minus 4. So we get d plus 1 into d minus 4 equal to 0. Separate that factor. So we get d plus 1 equal to 0, d minus 4 equal to 0. So we get d is equal to minus 1, d is equal to 4. So we get two roots of the auxiliary equation. And therefore, complementary function is c1 e raised to m1z plus c2 e raised to m2z, because here variable is z. Now put values of m1 and m2 here, and so we get cf is c1 e raised to minus z, value of m1 which is minus 1 and value of m2 which is 4. This is equation number 2. Now we have to find pi. Pi is equal to 1 upon f of d into z. Here f of d is d square minus 3d minus 4 into z. Z means e raised to 2z plus 2z. So separate this one. So this is equal to 1 upon d square minus 3d minus 4 into e raised to 2z plus 1 upon d square minus 3d minus 4 into 2z. Here 1 upon d square minus 3d minus 4, this is the operator. This represents the integration. As 2 is constant, so you can take that 2 outside of that operator. And so we get pi is equal to 1 upon d square minus 3d minus 4 into e raised to 2z as it is, plus these two constant outside of that operator. So we get 2, 1 upon d square minus 3d minus 4 into z. So pi is equal to this. So e raised to 2z, put here d is equal to a. If you put d is equal to a, if you observe that this denominator doesn't become 0. So put d equal to a here. So we get 2 square minus 3 into 2 minus 4. 2 square is 4. 4 minus 4 get cancelled. So in denominator we get minus 6, which is not 0. So use that result. So we get this is equal to this. This minus of, now in second term, see this denominator, take out 4 as a common. Minus 4 as a common, and so we get minus 2 by 4, 1 upon this 1 minus d square minus 3d upon 4, and this z as it is. And so pi is equal to e raised to 2z upon 4 minus 6 minus 4, 2 upon 4, which is 1 upon 2. Transfer this denominator to the numerator, and so we get 1 minus d square minus 3d by 4 bracket raised to minus 1 into z. As you know, 1 minus x bracket raised to minus 1 is this. So use this result again here, and so we get pi is equal to e raised to 2z plus 4 minus 4 get cancelled, so upon minus 6. e raised to 2z upon minus 6. This minus half as it is. Now use this result. 1 minus x bracket raised to minus 1 is equal to 1, then plus x, then plus x square, then plus x cube. Continue like this. So here x means d square minus 3d upon 4. So we get 1 plus x means d square minus 3d upon 4 plus x square means d square minus 3d bracket upon 4 bracket square, and we have to continue like this, and that outside is here. Now take this z inside 1. So this is equal to that minus sign e raised to 2z upon 6 minus 1 upon 2 this z plus d square minus 3d upon 4 into z plus d square minus 3d upon 4 bracket square into z plus dash dash dash. Here we observe that first derivative of z is 1 and second derivative is 0. In second term, here this value will become 0. All the values next to this one will become 0. And so we get pi is equal to minus of e raised to 2z upon 6 minus of this z, second derivative of z which is 0 minus 3, first derivative of z which is 1 upon 4. This term is 0 and next all that terms are 0. And so pi is equal to minus of e raised to 2z upon 6 minus 1 upon 2 z, and here we get minus 3 upon 4, so z minus 3 by 4. So this is the value of particular integral. Now as general solution is y is equal to complementary function plus particular integral, put both the values here, and so we get y is equal to c1 e raised to minus z plus c2 e raised to minus e raised to 4z, which is this here. Already we have find that one, so put that value here, and then value of pi which we have find here, and that value is minus e raised to 2z upon 6 minus 1 upon 2 into the bracket z minus 3 by 4. Now put here z is equal to log x, that is x equal to e raised to z. So e raised to z is equal to x, and so e raised to 2z is equal to x square. E raised to minus z is equal to x raised to minus 1, and e raised to 4z which is x raised to 4. Put all these values in this equation, and so we get y is equal to c1 x raised to minus 1 plus c2 x raised to 4 minus x square upon 6 minus 1 upon 2 log of x minus 3 by 4. Now here we observe that this is relation between x, y and constant. So this represents the general solution of the given homogeneous linear differential equation. We can write this equation like this also. X raised to minus 1 means 1 upon x. So you can see this equation. This is again a relation between x, y and constant. So this is the general solution of given homogeneous linear differential equation. See one more example. Now see the example which is reducible to the homogeneous linear form. See the first example. Solve 1 plus x bracket square d2y by dx square plus 1 plus x dy by dx plus y is equal to 4 cos of log of 1 plus x. We have to solve this differential equation. Write down that equation and give this equation number 1. If you observe that here is no term of x, here is the term of 1 plus x. So this is not a homogeneous differential equation. So first we have to transfer this to the homogeneous linear equation and then linear differential equation. So for that first we have to put 1 plus x is equal to u. So put u is equal to 1 plus x, that is x is equal to u minus 1. And therefore value of dy by dx is dy by du, and value of d2y by dx square is equal to d2y by du square. And therefore this equation 1 becomes u square d2y by dx square plus u dy by du plus y equal to 4 cos of log of u. Now observe this equation. This is the differential equation in two variables u and y, and here we observe that power of u and order of derivative in each term both are same. Means this is the homogeneous linear differential equation in two variables u and y. Now we have to solve this differential equation, means we have to reduce this equation to the linear differential equation. So we should put z is equal to log of u. Instead of x, here is u. So we should put z is equal to log of u. That is, u is equal to e raised to z and capital D as d by dz. And then u into dy by du will become capital dy, and u square d2y by du square will become d into d minus 1 into y. And therefore this equation 2 becomes d into d minus 1 into y plus d into y plus y equal to 4 cos of log of u, which is z. So we get this one. Take out y as a common and d inside 1. So we get this one plus d minus d get cancelled. So we get d square plus 1 into y is equal to 4 cos of z. Now observe that this is the differential equation of the type f of d into y is equal to capital Z. So this is the linear differential equation. So its associated equation is d square plus 1 into y is equal to 0. And therefore auxiliary equation is d square plus 1 equal to 0. Actually this is f of d is equal to 0. This is the auxiliary equation. Now we have to find the factors of this. So d square plus factors of d square plus 1 are d plus I, d minus I. Here we use the result factors of a square plus b square, which are a plus ib, a minus ib. And so factors of d square plus 1 are d plus I into d minus I equal to 0. And so we get d is equal to minus I and d is equal to plus I. Means we get d is equal to plus minus I. That is, we get here complex factor. We can write this plus minus I as 0 plus minus I. 0 means alpha and 1 means beta. So we can write this is alpha plus minus I beta. So comparing this, we get a value of alpha as 0 and value of beta is 1. As this is a complex factor, this auxiliary equation has complex factor. So complementary function is given by e raised to alpha into z into the bracket c1 cos of beta z plus c2 sin of beta z. Now put the values of alpha and beta here. We get CF is equal to e raised to 0 into z into the bracket c1 cos of 1z plus c2 sin of 1z. We put the values of alpha and beta here. And so e raised to 0 into z means it is e raised to 0, that is 1. So we get 1 into c1 cos of z plus c2 sin of z, that is CF is c1 cos of z plus c2 sin z. This is equation number 3. Now we have to find Pi. Now Pi is equal to 1 upon f of d into z. So this is equal to 1 upon f of d, which is d square plus 1 into z, which is 4 cos of z. Take out this 4 outside of that operator, and so this is equal to Pi is equal to 4 1 upon d square plus 1 into cos z. Here we have to put d square is equal to minus a square. What is a? A is 1. As a is 1, so a square is 1. So minus of a square means minus 1. If we put d square is equal to minus a square, here denominator becoming 0. And we know if denominators become 0, we have to use that second result. 1 upon d square plus a square bracket raised to r cos of ax is given by minus 1 raised to r x raised to r cos of ax plus r pi by 2 upon r factorial into 2a raised to r. Here value of a is 1 and value of r is again 1. So we have to use this result because here denominator becoming 0. Instead of x, here is z. So first transfer this in terms of z, and so we get here Pi is equal to 4 minus 1 raised to r, x means z, z raised to r, cos of az plus r pi by 2 upon r factorial into 2a bracket raised to r. Now put the value of a and r here. Value of a is 1, value of r is 1, and so Pi is equal to 4 into minus 1 raised to 1, z raised to 1, cos of a into 1 plus r means 1, 1 into pi by 2 upon 1 factorial into 2 into 1 raised to r means 1. Minus 1 raised to 1 is 1, 1 factorial is 1. So you can write Pi is equal to 4, this minus sign z cos of z plus pi by 2 upon 1 factorial is 1, 2 into 1 it is 1, 2. So 1 into 2 it is 2. So we get Pi is equal to this. Therefore, Pi is equal to 4 upon 2, it is 2 z, and that minus sign inside 1. Minus of cos of z plus pi by 2, we write like this. 4 upon 2, it is 2. This z outside. Inside we get minus cos of z plus pi by 2. And you know, minus cos of z pi by 2 is a sin z. Because you know the formula cos of pi by 2 plus theta is equal to minus sin theta. Transfer that minus sign to this side. So minus of cos of theta plus pi by 2 is sin theta. So here we get sin z. So Pi is equal to 2z into sin z. Already we have find complementary function. Now we find Pi. So general solution is given by y is equal to Cf plus Pi. Put the value of Cf and Pi. So we get y is equal to C1 cos of z plus C2 sin of z plus Pi, which is 2z sin z. Now put value of z as log of u. So we get y is equal to c1 cos of z means log u, c2 sin of log u plus 2 log u sin of log u. Now put value of u in terms of x, which is 1 plus x. So instead of u, write down 1 plus x. So here we get y is equal to c1 cos of log of 1 plus x, c2 sin of log of 1 plus x plus 2 log of 1 plus x into sin of log of 1 plus x. Now observe that this is relation between x, y and some constant. So this represents the general solution of the given differential equation 1. So we should stop here now. Dear student, stay home, save lives, take care. Thank you.